let's assume that the collision represented by this problem we just solved takes place in 1/100th of a second. That is, it takes 100th of a second for the two objects to hit together and bounce off. We want to find the average force exerted between the objects. Well, we see that the first object loses 1,700 gram-centimeters per second of momentum, and the second object gains 7,300 gram-centimeters per second of momentum. We can apply the impulse momentum theorem to this situation. Remember, the impulse momentum theorem says that the average force times the time interval over which the force is applied is equal to the change in momentum. Okay, so this is called the impulse, F bar delta T, average force times time interval, and delta P, of course, is change in momentum, and they're equal by this impulse momentum theorem. Now, if delta P is 1,700 gram-centimeters per second, of course that's the delta P of the second object, the delta P of the first is negative 1,700 gram-centimeters per second, but this at least gives the magnitude of the delta P. Then, if delta T is 1/100th of a second, which is a fairly typical time of collision for objects that are moving at a relatively fast speed, relatively hard objects, then the force is delta P over delta T, and there should be a bar over that force. It should be average force. And that's going to be 1,700 gram-centimeters per second over 0.01 seconds. And of course that divides out to 170,000 gram-centimeters per second. Now a gram is 1,000th of a kilogram and a centimeter is 100th of a meter. So a gram-centimeter is 100,000th of a kilogram-meter. Of course you can use standard calculations, standard unit calculations to do that, but that's the common sense of it. It takes 1,000 of these to make one of these, and 100 of these to make one of these, so it takes 100,000 of one of these to make one of these. So we're going to have a lot fewer of these than we have of these. And the factor is 100,000, move the decimal over 5 places. We have 1.7 kilogram meters per second squared, and that's 1.7 newtons. By contrast, if delta T was 1,000th of a second, if these objects hit really quickly, then the average force would be 10 times as great, because we'd be dividing by 0.001 instead of 0.01. That would give us a number 10 times as great here, and our average force would be 10 times as great here.